Hello guys. So as we have already started our discussion on the strength of material, in that continuation only we will be learning in today's basically lecture, that is a thermal stress and strain, right? So this is our lecture number 4 as we have started in the strength of material, that is for the crash course of aerospace. In that only we are continuing with this topic, and this is one of the most fundamental and important topic, right? Thermal stress and strain, that is what we have to discuss, right? So we're gonna put first of all the heading, thermal stress and strain. We will try to learn the fundamental things regarding this topic so that we can basically cover the fundamental as well as we can solve some few numerical based on this topic, right? Very first of all, my dear friend, when I just basically pinpoint about the thermal stress, then we already know much about the detailing about the thermal stress. Means we know already much more detail about the stress, right? That is the internal resistant force developed per unit area. Internal resistant force developed per unit area, that is called stress, right? So whenever you either you apply the load or you just change the temperature, working temperature of the body. In both the scenario, my dear friend, there will be stress will be generated in the body, right? So here basically I will classify the stress under two categories. One is a mechanical stress, and then we will classify under the thermal stress, right? So if I just talk about the basic stress, then we have the mechanical stress, and then we have the thermal stress. Then we have the thermal stress, my dear friend. Now you try understanding what I'm talking about. In thermal stress, my dear friend, whenever you just say total stress developed on the cross section of the member, then always you represent it by both these stresses, right? So put a note, a very, very important note. What I am discussing right now, I will be discussed, basically, theoretical manner as well as we will be discussing by the formula also. So total stress, the total stress, my dear friend, on a cross section of the member will be equal to mechanical normal stress plus thermal stress. So total stress on a cross section of the member will be mechanical normal stress plus thermal stress. But what about the mechanical normal stress? Mechanical normal stress basically developed due to the load acting on the cross section of a component, right? What I'm just saying, this mechanical component of the stress will be generated due to the load, acting on a cross section, of a component, right? So this is one of the important thing. When you just apply the load, body will try to resist that load. During that resistance only the stress will be generated. That is nothing but what? Mechanical stress. So what about the thermal stress? Sir, what about the thermal stress? That is what we have to discuss. See, if you are, suppose you have taken any body, and you are just working, applying the load at a temperature, let's say 25 degrees centigrade, that is surrounding temperature. Like, in a particular laboratory of this farm, you are maintaining the temperature as 25 degrees centigrade. That means there will not be any thermal stress if you are not changing the temperatures, right? So for generating the thermal stress, for developing the thermal stress in a component, in a material, first criteria should be there should be some temperature variation. There shall be temperature variations. That is the most fundamental requirement of the thermal stress to be generated, right? Because not only the temperature variations, delta T, I'm talking about delta T. You will see in the formula also, delta T is coming. So there's no doubt that, sir, in the basically theoretical aspect, we are saying that, but formula wise, can we prove that? Yes, we can prove that, right? The second requirement will be the above thermal deformation. Above thermal deformation should be restricted either partially or completely. Sir, what you are talking about? Second point, thermal stress, I just talked about. If I just write over continuation only, that second point, let me write here. This is a requirement, that is the second requirement of generating the thermal stress would be the above thermal deformations. See, because of the temperature variations, there will be some there will be some thermal deformations, right? So the above thermal deformation, the above thermal deformations because of because of temperature variations, because of temperature variations shall be restricted either partially or completely, right? Whenever you talk on any member, any material you take, there will be two types of stress: mechanical normal stress and there will be thermal stress, right? So we will be discussing about the how we can just prove that this is statement about the thermal stress. Let's see. Now understand, suppose my dear friend, it's a property of the material, right? Sir, what is the property of the material? For example, I'm just taking one example. There is a one rod which is just placed in an environment conditions, not in the air, with the, some kind of on the bench or something, we have placed it, right? And now for this rod, I have just increased my temperature. Delta T I have increased. For example, I'm talking about, for example, temperature can decrease also, right? In a very basically in a cool environment, the temperature can decrease also, right? Yeah. So this particular material, my dear friend, what I will be doing when I just increase the temperature, then what will happen? There will be some kind of deformation will happen for this material. There will be some kind of deformation will happen for this material. So what is this? There will be thermal deformations. As we are not applying the any kind of load, that there will not be any axial deformation as of now. Only we are increasing the temperature. Only we are increasing the temperature. That's why what I'm saying that because of increment of the temperature, there will be some elongation in the length side as well as in the what other side of the dimensions. L, the final length will be more than that. Whatever the width will be there, that is also more than the original width or thickness of the material, right? So what is this delta? Change in length. The total final length is what? Maybe LF plus delta L. Sir, whatever the change in length is there, this is the final length. For example, this is now my final length. This is the initial length, right? So whatever the final length minus initial length is there, I'm calling this to be delta L. Sir, what is this formula? The formula will be alpha into delta T into L. Alpha into delta T into L, right? Sir, what is this alpha? Alpha is nothing but coefficient of thermal expansion. Coefficient of thermal expansion. Right? This is the material property, one of the very, very important. This is the material property. Second thing will be delta T, that is change in temperature. Li will be original length. Lf will be the final length. Right? So note down, these are the very, very important thing regarding this. Now, my dear friend, this whatever the this thermal deformations which are happening, This thermal deformation, this one. Okay, thermal deformation is happening, that is good. But this thermal deformation will cause any amount of stress. That's a question mark. That's one of the big question mark. Whatever the thermal deformation, what we are observing, whether this will cause any amount of any kind of internal resistant force to be developed in the material. Let's see. That is the point of discussion. Right? Unlike what you have seen when we have the axial deformation because of the loading conditions, sure shot guarantee is there until unless there is a support. Means if there is a support, there will be some kind of stress. When there is a support, there will be some stress. Whenever there is a restriction, there will be some stress in the material. Let's see for this case. Right. So this is what we are discussing, our cases by cases about this thermal stress studies, right? No. Case number one. Note down my different case number one. This is a very important. The case number one I am calling is a free expansion case. A free expansion. I will connect the dot. I know that right now you might be having so much of confusion, but no need to worry. Note on the first case, that is a free expansion case. Free expansion or free contraction, whatever you can call. Let's see, my dear friend, I'm just taking one slab, one body, which is nothing but a plate. Plate kind of things I can take, where I can show all the three dimensions. This is L, this is B, width, and this is nothing but thickness, right? My dear friend, this was the original at a temperature T. But suddenly I increased the temperature like anything, like delta T. I have increased the temperatures. Definitely there will be some elongations. Definitely there will be some elongations. Alpha into delta T into L. Delta B will be what? Alpha into delta T into B. Delta T will be what? Alpha into delta T into T. There will be deformation in all the three dimensions, lengthwise, widthwise, and thickness-wise. Right? Now let me show it by the diagram so that you can visualize what I'm talking about. See, understand. Try understanding what you mean. When you see that there will be some expansion, this kind of material will basically what? Whatever the property of the material is there, based on that, there will be some kind of deformation in lengthwise, widthwise, and thickness-wise, as you can see very clearly. Right? So this will be my final length. This will be my final width. And this will be my final thickness, my dear friend. Right? Now, so because of the free expansion, there will be some strain. See, whenever we have the deformation, we know that from our basic concept, strain is what? Change in dimension by original dimension. That is what we have learned, the fundamental things. Change in, see, fundamental cannot change, as you change the loading condition, either you apply thermal load or mechanical load. The basic fundamental of the stress and strain will not change, right? The definition will not change. Change in dimension by original dimensions. By original dimensions. What are the change in dimensions which are happening, my dear friend? Change in dimension, suppose delta L divided by L. This I'm calling epsilon x, because see, let me just put the coordinates so that it will be very easy for you to identify. Let me call this to be x, this to be y, and this is to be z, my dear friend. Let me make it three figure kind of thing so that you can visualize. This will be z. So whatever the along the x directions, whatever the Basically the dimension is there that I'm just denoting by delta L, that is the length. So this I'm calling epsilon x. Sir, what is the formula? Change in length, alpha into delta t into L divided by L. This will cancel out, so alpha into delta t. What about the strain in the y direction? My different change in width divided by original width. Sorry, change in thickness divided by original thickness, because in the y direction we do have the thickness. So change in thickness divided by original thickness. So what I'm got alpha into delta t once again. Similarly, you'll be getting alpha z also, epsilon z also as alpha into delta t. So epsilon x equal to epsilon y is equal to what? Epsilon z, that is equal to alpha into delta t. This is called a thermal strain. No doubt, this is a thermal strain. This is a thermal strain, not a mechanical strain, not a longitudinal strain. No doubt, not a longitudinal strain. It is not a longitudinal strain. It is a thermal strain. Be very, very careful. What is the longitudinal strains are? Already we have discussed, my dear friend, right? See, whenever we have the rod, we are applying the load, something like this, for example. Then in the direction of applied load, whatever the strain will be generated, in the direction of applying load, whatever the strain will be developed, that is called a longitudinal strain. Perpendicular to the dimension of the load, perpendicular to the load, whatever the changes are happening in the dimensions, we call that to be a lateral strain. In case of thermal loading condition, my dear friend, there will be no such a kind of scenario what we have discussed, a longitudinal or lateral strain. Here we will be simply calling it as a thermal strain. First thing you just keep in your mind. Getting my mind? Now, sir, what is the nature of this strain? Tensile strain, right? Because in all the directions, there will be some increment in the dimensions. So what I'm calling, this is to be a tensile strain. Not a compressive strain. There will be some tensile strain will be developed in the material, right? Make a note of it. For the case number one, alpha is a mechanical property, alpha is a mechanical property, alpha is a mechanical property. Everybody know that. Everybody know that alpha is a mechanical property. When everybody know this is a mechanical property, and you change the temperature also, when you change the temperatures, material wants to expand. When you just increase the temperature, material wants to expand, right? If the material itself want to expand, if the material itself by its own wishes try to expand, and we are allowing it to expand, we are just allowing, basically what, allowing that particular material to expand, that means what, there will be no stress. What I'm just saying, I'm talking about the stress strain we have discussed, right? For the case number one, for the case one, the material itself, wants to expand, because see, when we increase the temperature, the moment we increase the temperature, my different alpha is there. Alpha is a mechanical property. Alpha is a what? Property of the material. Alpha is a property of the material. Definitely material will try to expand. There is a, nobody can stop that material to expand. It's a property. The material itself wants to expand, and we are allowing, we are just allowing it to expand. Then why material will resist? Then why material will resist? Why material will resist? No resistance. No resistance, there will be no strain or no stress. No resistance means what? No stress. So free expansion is nothing but a no stress condition, my dear friend. That means sigma thermal stress in X direction, sigma thermal in Y direction, sigma thermal in Z direction will be 0, my dear friend. Sir, what is the meaning of you are allowing to expand? See, just now I told you we have just being restricted the material. For example, my dear friend, for example, suppose we are not allowing it freely to expand. We are not allowing expand it to freely, like in a very easiness. We are not allowing that. We are just superimposing some kind of support reactions, right? Now there's a support. This support will say, now you cannot expand freely, my dear friend, because there will be some kind of reaction forces. There will be some kind of reaction forces. Rx, Ry, and Rz will be coming into the picture. Earlier case number one, there is a no such a kind of support reaction. Whatever the support reaction is there, from nowhere where the support or reaction is coming, that okay, we are not going to allow it completely freely expand it. No, but here you can see that there is a no such a kind of restrictions. No such a kind of restrictions. Material is freely expanding like anything. But here what you can see in this particular scenario, my dear friend, the material is not. Material is placed, the temperature has been increased, but it is not allowed freely to expand, because some restriction is there. Because of the what? Why the restrictions are coming? Because of the support reaction forces, right? So indirectly I can say Rx, Ry, and Rz was 0 in our first case. There was a no reaction forces. Material was freely try to expand. Material wants to expand and we are allowing it to expand. What is the Newton's first law? If the body is in the particular state of a rest condition, it will remain under rest conditions. That is the law of inertia. Same thing is happening over here also. Initially, before changing the temperature, body was saying that I am just at the key, I am just at the basically what? Calm positions. Don't try to disturb me. Okay, that was the conditions set by the material. But the moment you try to superimpose some condition like temperature, you change it, then material will say, okay, you change the temperature and you are just not we are not finding any restrictions. Okay, no problem. That is also basically what? Law of inertia. If the material wants to move and you are just basically providing some driving force for the flow, and the Y material will resist. And I told you, stress is what? Internal resistant forces. No resistance, simply no stress. That is about the first case. That is the free expansion case. So that's why, my dear friend, it is well said before that in one of the in many of the textbooks you will find that stress can be generated. Stress can be generated. What means, if I just talk about the among stress and strain, which is an independent parameter, strain is an independent parameter. As you can see, strain is developed without having any value of what? Stress. No stress, but strain is there. No stress, but strain is there, right? But in reverse manner, you cannot find. In reverse manner, you cannot find. The moment if I say strain is 0 and you say that stress is there, it is not possible, right? So stress is dependent on the strain. Strain is not dependent on the what? Stress. Getting my point? So this is one of the important point. That's why we plot x-axis strain, that is the independent parameter, and the y-axis we plot stress, that is the dependent parameter, right? Now, so let's discuss about the case 2. That is nothing but a partially restricted case, or maybe we can discuss about the completely restricted case. Just now I told you, one case, this one. Maybe you can just expect similar kind of case 2, right? Case 2, completely restricted case. Completely restricted case. One of the very easy one. Try understanding. Earlier, my dear friend, we place the material like this, right? But now we place it in between the support. Now we will place it in between the supports. Something like this, right? Earlier, you might have placed against the some support only, but you just not have the support onto the other side. and you just increase the temperature, and the material will say happily he will just expand it like anything. It was simply expanding like anything, but right now it's a completely restriction is there. Completely restriction is there. And remember, it is a rigid support. Remember, it is a rigid support. It is a rigid support, my dear friend. Let's discuss, sir, once each and every part. That is a D, L. Now, try understanding. Try understanding. I will be telling you the method which are very much suitable for this case. Support, whatever the rigid support is there, you assume that it is not there in the first case. So what I'm just using superposition principle. Superposition method. What is the superposition method, my dear friend? You just take the support and you just, basically what I'm just saying, you just increase the temperature. After increasing the temperature, my dear friend, what will happen? The material will try to expand like this. Material will try to expand like this. Nobody can stop. Once you remove the support, nobody can stop that material to expand, right? But what will happen, my dear friend? What will be happening after expanding to this much of distance? Now put the support back. Put the support back to the structure. Then what the support will say? Hello, go back. What it will say? Hello, go back to the what? Original positions. Initially, you just remove the supports. What is the principle of superpositions? Analyzing the structure by superimposing different loading conditions. That means in first case, we will take not the any kind of any rigid support, just a free expansion case. It will freely expanding. But after some point of time, we will be just putting the rigid support back to the picture, and it will offer some kind of reaction forces. Reaction forces. Reaction forces. And what you are observing, my dear friend, what you are observing, because of this there will be some delta 1, because of this mechanical reaction forces there will be some delta 2. No problem. Yes, at the end of the day you superimpose these two conditions, and the final condition should be what we have discussed. It should be just to the come to back to the original position. That means total change in the length has to be 0. Total change of the length has to be 0. First, we will assume that there is a no rigid support, and we will just allow the material to expand freely, happily, and after a point of time, some point of time, we will place the support back, and it will offer some kind of reaction forces, as everybody know that, right? And my dear friend, what we are observing, what we are observing, my dear friend, try to understand very keenly and patiently that delta 1 plus delta 2 has to be 0. So delta 1, thermal deformations, because temperature variation, thermal deformations, that is alpha into delta T into L. Alpha into delta T into L. Positive or negative? Positive, sir. Because of the compressive force, because of the compressive reaction forces, everybody know that what is the axial deformations? P into L divided by A. Suppose any material is there and we are just applying the load P, having a length L and having a diameter D, then PL divided by A, that will be the axial deformations. That will be the axial deformation, my dear friend. Here, what will be the axial deformations? Minus of what? R into L divided by A. That is equal to 0. From here, what you will be getting reaction forces? Alpha into delta T into E into A. Once you got the reaction forces, my dear friend, this reaction force and this reaction force, suppose A point and B point, both the reaction forces will be same because there is no intermediate support, intermediate load, right? And everybody know that what is the stress? Once the internal resistant force will be developed in the material, once the internal resistant force will be developed in the material, then we know that load divided by area, not simply the load, resistance force or resistance load divided by area. That means alpha into delta T into E into A divided by what? A. Finally, thermal stress is what you have, my dear friend, alpha into delta t into E. Remember one thing. This is not the mechanical stress. This is the thermal stress. And why we are calling this to be a thermal stress? Because you don't basically just misunderstood that we are applying some kind of reaction force. No, 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 no. Just we increase the temperature. That's why the reaction force is coming. It is not happening individually or independently. That's why we are calling this to be a thermal stress, not a mechanical stress. Make a note of it. Right? So this is a completely restricted case, my friend, right? And as you can see, thermal stress is what? Delta T proportional. Now, what is the nature, sir? Nature will be decided just the direction of reaction forces. As the direction of reaction forces are what? Compressive in nature. That's why thermal stress will be what? Compressive. Compressive, my friend. Very, 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 very important. Right? Now, in a very similar fashion, we're gonna have the case number 3 also. Case number 3 also. That is a partially restricted case. Partially restricted expansion. Yeah, one more thing. Suppose if I drop the temperature, suppose if I drop the temperature, then what will happen? If I drop the temperature, then material will try to contract. Suppose, for example, right? In the first case, what you say, delta 1, what was alpha into delta T into L? But you just kept the what? Support. You just kept the support, right? Support will say the final length has to be 0 because you are fixed at both the ends. The length cannot change. This L cannot change. So what the support will say? Come back. Come back. And due to that, when the temperature will be getting decreased as compared to the final initial conditions, whatever the temperature is there, if it is getting dropped, there will be some kind of tensile stress will be developed. So what you can just note in a short, you can note down if delta T increased, compressive stress. Compressive stress. If delta T decreases, tensile stress, right? That's a very short thing we can just remember about the sign. Partially restricted expansion or contraction. Understand a very simple case in one directions, in one particular directions. Now, suppose my dear friend, we have the material. This is a material we have, which is having a length L. Now also we just place it in the supports. In between the two support, we have placed it. Sorry, in between the two support we have placed. But this support, right support, is not a rigid support. I'm calling this to be a flexible support. Flexible support. This is not a rigid support. This is a flexible support, my dear friend. That means it can just, basically, it can displaced by little amount, right? It is not like a rigid support which cannot be deformed. It can deform, right? Now, again, we're gonna use the superposition principle, my dear friend. So very first thing, what will happen? Very first thing, what will happen, my dear friend? Now, try understanding. We're gonna put the material, and we are just saying that this flexible support now has been displaced by lambda amount. What is the lambda? The expansion permitted by the support. The expansion which is permitted by the support. What is the meaning of that, sir? Understand. This is the length L, right? Initially, what will we do? What we gonna do, my dear friend? See, both the diagrams are related to what? Case number 3 only. Flexible support means the support which can displaced by the amount lambda as compared to the original conditions. Now what you do, just start increasing the temperature. You just start increasing the temperature. When you just start increasing the temperature, my dear friend, what the material will do? Material will try to expand it. Happily, it will expand like this. And how much of expansion will be there? That is a material property. That is a material property. We cannot have the control over it, right? Once we increase the temperature, then it's totally dependent on the material, how much it want to expand, right? Now, but there is some kind of support. There is some kind of support. What the support will say, my dear friend, you can just have the expansion, but not that much as you are expecting. That completely expansion won't be provided. Whatever you are expecting, that once I increase my temperature and you are expecting that alpha into delta T into L, that much of expansion will be there. You are wrong. That much of expansion will not be there. We will be slightly allowing you to basically expand by the amount lambda, not completely, right? Then support, what the support will say, go back. What the support will say, just to go back by this amount. By which amount? This amount. By which amount? This much amount was what? Alpha into delta T into L. And we are just allowing what? We are just allowing only lambda. So this much of restriction is there, right? How much of restriction is there? Alpha into delta T into L. You cannot have that much. Only you can have what? By which amount? By which particular amount you can have the expansion? Only by lambda, right? So what I can say, my dear friend, for the material, the total restriction, total deformation will be, now the total deformation will be lambda, not zero. Not zero. In earlier case, we have seen that total deformation was zero. The rigid support was not allowing the material to expand, but completely, right? But here you can see, my different, the material, whatever the support is there, it is just saying that you can just expand by the amount lambda. In this, we have lambda 1, delta 1 plus delta 2, that is equal to what? Lambda. What is the delta 1? Thermal deformation, that is alpha into delta T into L. And what is the delta 2? That is the mechanical deformation, that is nothing but what? R into L divided by AE. When you just solve it, you're going to get RS alpha into delta T into L minus lambda into E by L into A. Just like a same previous formula, but in the previous case, we have not seen any lambda. No expansion was permitted. But here we have provided some kind of what? Expansion, my different. Right? Total deformation is what? Alpha into delta T into L minus of what? Some amount of restriction has been provided by the flexible support. Right? Make a note of it. This is a restricted deformations. And because of this restricted only, which is nothing but alpha into delta T into L minus lambda. Because of this only, the whatever the resisting force will be there, that will be developed. And what is the stress? R divided by area. R divided by area. And what is the nature, sir? Nature will be compressive stress. Make a note of it. Very, very important. So first case, we have discussed the free expansion case. In the free expansion, we have seen that there was no such a kind of support. The material is expanding freely. and whatever the external agency is there, or the material who is handling that material, he or she is just allowing the material to expand freely. So there is no stress. Yes, strain will be there, right? But in the case number 2, we have seen that we are not allowing any amount of deformations. The net final length, whatever is there, that has to be initial length. That has to be equal to initial length. No change in the length has been provided for that material, right? In the case number 2, if I just go back and just take you back to the case number 2, whatever the final length is there, that is equal to what? Original length. So there was a no amount of basically what? Deformation has been permitted. That's why we have taken what? Total deformation to be 0 in x direction. In x directions, right? The total deformation we have taken what? Equal to 0, right? In case number 3, what we have done? We have done the partially restricted. That means whatever our rigid support is there, that has been replaced by the flexible support, which can displace by the amount lambda, right? Now in examination, they can play like anything. They can put the restriction. The case number 3 questions can be asked in many ways. The partially restricted one is there, no? Lambda, that lambda can be replaced by the spring. Something like this. This lambda will be what? The deformation is a spring. Right? If you just change the temperature, my friend, this body, the body will try to expand, the spring will be getting compressed, but whatever the final length is there, whatever the total change in the length is there in the bar, that will be delta of spring. So it is just working like a what? Lambda only. Either the problem can be asked in this way, or the problem can be asked in this particular manner also. Okay, we will see. I think just wait. We will see that case through question. I just want to say that you have the feeling that, okay, the case number 3 is a partially restricted case. So if I place the spring, that will be a very similar question, basically cases of case number what? If I place the spring, that will be a very similar case, just like a case number 3, right? Now, but precaution. Precaution in case number 2, case number 3. In case number 3, we have seen the body was placed like this, right? The body was placed under the impression of lambda. That means this lambda deformation is permitted, right? This body is having a length L, diameter D, something like this. Now, this is the flexible support. But if the deformation, because of temperature changes, whatever the expansion is there, this expansion is less than lambda. This delta L alpha into delta T into L. If it is my different less than, if it is less than the lambda, if it is less than lambda, there will not be any thermal stress. The thermal stress will be 0. The material is freely expanding. The material is not touching the support. The material is saying that, okay, because of the property of the material, my alpha is very, very low. And even though my alpha delta T into L combined together, we are calling just 5 mm, and you are just permitting lambda suppose 10 mm. For example, we are freely expanding. When we are freely expanding, nobody can is stopping us. If the support would have been here, then we say that, okay, you cannot expand. But right now you can see that support is far away from the free expansion case, right? Means this particular deformation 5 mm is what? Free expansion kind of things. So for case number 3, to have thermal stress not equal to 0, alpha into delta T into L must be more than lambda. Then only it will be hitting to the right support like anything. When it is just hitting the right support, then only the Newton's third law will applicable, then only the Newton's third law, reaction forces by the support will be coming into the picture, Getting my point? Now, thermal stress, that is a mechanical plus thermal, right? What about the strain? Strain due to thermal loading, I told you, will be same in all the directions, right? Mechanical strain, everybody know that for triaxial loading case, we have seen that epsilon x is equal to what? Sigma x divided by E. Here they have written mu. You can write mu also and you can write mu also, right? Same thing, nu or mu, right? If I club together thermal strain and mechanical strain, I will be getting what? This one, my friend. Epsilon x, epsilon y, epsilon z. This is the total. If a component is subjected to both mechanical and thermal loading, then both will be coming into the picture. Sir, what is this case? Can you just please a little bit elaborate? Yes. Suppose you have the things, you are applying the load P, basically to L by 4 and 3L by 4, and you are just increasing the temperature also, right? So in that scenario, you will be having both mechanical stress and thermal strain and mechanical strain. Not only with that, you will be having thermal stress as well as mechanical stress also. You will be having mechanical stress also because load is there, Sir, how to solve that? This is a beyond the scope of, yeah, we have in the syllabus, but in gate examination, it's very tough to deal with the what for given amount of time, that is 3 minutes, right? So you can just solve it by principle of superpositions. By principle of superpositions. By that particular concept, you can solve it. Let's solve some example. A circular rod, metallic rod of the length L, that is 250 mm, is placed between the two immobile walls, right? The immobile means that particular, now whatever the support is there, that is just like a rigid support. Whatever the rod is there, it can only deform up to the amount what? 0.2 mm, right? Now we have to find the axial stress which is being developed because of temperature has been changed, right? The temperature has been changed. As you can see very clearly, the rod temperature has been increased by what? 200 degrees centigrade, right? So first of all, calculate alpha into delta T into L. What is alpha? 10 power 5 minus 5. Delta T is what? 200. E is what? 200 into 1000 megapascal. 1 gigapascal is what? 1000 megapascal, right? So when you do the calculation, what you will be getting, my different 10 power minus 5 into 200 into 200 into 1000. You will be getting, my different, alpha into delta T into L. That is coming as 400 mm, which is more than zero point 0.2. So what about the thermal stress? Everybody know that alpha into delta T into L minus lambda into E by L. Just wait, just wait. Oh, sorry. Just a moment. We have placed here wrong values. Alpha delta T is what? 200. Length is what? 250, right? So I just placed the values of what? Young's model. That is incorrect. So I'm getting 0.5. 0.5 mm is what? More than 0.2 mm. Definitely thermal stress will be developed into E into 1000 divided by what? L. So you will be getting what? 240 megapascal. When you calculate thermal stress, you will be getting what? 240 megapascal. Right? Very, very important. Make a note of it. Now try to see this particular question. A rectangular plate of uniform thickness having the initial length A and width B is placed between the two immovable walls. The temperature of the walls is increased by delta T. The plate is free to expand along the Y and Z directions. The plate is free to expand along the Y and Z directions. Y and Z directions. That means there is a restriction only in the X directions. There is a restriction only in the what? X direction. This direction we have the restriction. Y direction it can expand freely. There is a no support reactions. In Z direction that is a perpendicular to the plane of the board, no support reactions. Right? What they are asking, what is the change in the length of the plate after increase in the temperature? That means they are asking what is the delta A. What is the delta A? They are asking, my dear friend. That's a very simple question. Try understanding one by one. My dear friend, very first thing, if I'll be asking you at this point of time, material is free to expand in the Y and Z direction. That means what? Sigma Y will be 0, sigma Z will be 0. No problem. Because it's a free expansion case in the Y and Z directions. In X direction, no, it is not going to be 0. It is not going to be 0 because there is some rigid support has been placed. Perfect. Now, we also know that it is a completely restricted case. It's a completely restricted case. So epsilon x total epsilon x will be 0. So total epsilon x mechanical plus thermal both together equal to 0. Sir, what is the mechanical stress in x direction? Everybody know that. What is the mechanical stress? Epsilon x sigma x by E minus mu into what? Sigma y plus sigma z by E. All together this is 0. So what is the epsilon x? Sigma x divided by E. Sigma x divided by E. Alpha. What is the thermal deformation, sir? What is the thermal deformation, sir? Thermal strain will be what? Alpha into delta T. That is equal to 0. So what is the sigma x? Minus alpha into delta T into what? E. And by nature of the sign, what you are understanding? That is the compressive nature. That is the compressive nature. Okay, that is what we no need to find, but we have to find the values of what? Delta A, final change in the length. That means what? Total, we have to find total strain in the Y directions, right? Total strain in the Y direction, we have to find it out. Total strain in the Y direction, we have to find because A is what? Dimension in the Y directions, see very carefully. So in the Y direction, we have what? Mechanical and thermal, both is there, right? So what we can write, my dear friend? We can write what is the epsilon y in mechanical? Sigma y divided by E minus mu into sigma x divided by E minus mu into sigma z upon E. This is 0. This is 0. Plus what about the thermal deformation, sir? Thermal strain in the y direction, alpha into delta T. Getting my point? So finally what we are getting, my dear friend? Finally what we are getting? Total strain. Finally what we are getting? Total. See, I'm writing over here. Total, now I'm getting the values as minus mu into sigma x upon E plus alpha into delta T. Minus mu upon E, sigma x. Sigma x is what? Minus alpha into delta T into E plus alpha into delta T, that is equal to change in length by original length, right? In the direction of Y. So here I'm getting what? My dear friend, E will cancel out. So I'm going to get value as alpha into delta T 1 plus mu. This will be delta A divided by A. So what is the delta A? A into alpha into delta T 1 plus mu. B is correct. So that's a very simple procedure, right? Even though you don't know anything, but you need to be a little bit precautious in putting the values of sigma x. Sigma x in this particular formula, you have to keep it with this sign. With this sign. If you only say that completely restricted case, then sigma x will be, sir, alpha into delta T into E. That is correct, but only magnitude wise. You're not telling the directions. You're not telling the basically with the directions, whether it is a compressive or tensile. We know that in this direction there will be some kind of compressive stress will be developed because temperature has been increased, right? So that is all about the thermal stress, right? We have lot many cases that will be basically we used to cover in the what full course, right? Means full crash course. Thank you all.